It's great to be here to have a chance to share with you the first results from our work at the VLA. So this is a somewhat complementary strategy to going after this the FRB problem. So I'll try to describe that to you. But in a nutshell, the RealFast project is a commensal, real-time data analysis system that's focused on fast radio transients at the VLA. So the VLA is one of the world's largest radio interferometers based in New Mexico, 27 dishes, exquisite sensitivity, and recently refurbished through the enhanced VLA project back about 6 or 8 years ago now. So what the RealFast is basically adding a dedicated compute cluster to the back end of that interferometer. So this work done in collaboration with a number of people based at the NRAO. West Virginia University is a big part of this group, led by Sarah Burke-Spoler, and also actually Xavier Prochaska is here also as part of our team working on the optical side. So let me get started. Introduction to FRBs probably needs no introduction in the context of this meeting, but just briefly I'll say that we have a rich vein of information to mine from the basic traditional data analysis of fast radio transients, time versus frequency. This dispersed chirp comes down, and that helps us to access and infer information about the propagation, because radio waves are all kind of floppy in the way I imagine them. They're always kind of interacting with their environment or the things that they pass through along the way, and that is either a hindrance to their discovery, but once you discovered them, they give you exquisite ability to infer the nature of that propagation path. We've heard a lot about that even already from the first few talks. But all of that value really comes only when you've been able to associate the radio burst, which is itself sort of not tremendously informative. You want to associate that with that host, which is out here in the distant universe. And so once you can do that, you can take all these line integrals and make them into volume measurement quantities rather than mean quantities. So that's the basic name of the game for FRB localization, as we all know. So the VLA does this well because its localization precision is quite a bit better than any single-dish telescope, and is at the scale that is able to make unique associations to any distant host galaxy out to redshifts of even as high as, say, a redshift of 2, where you might have a lot of confusion for localizations of poorer than an arcsecond or so. And if that's all not exciting enough for you, we have also bridged the pop culture divide through some of my favorite sources of humor. So, The Onion and XKCD. But my favorite is this quote here: "It's humbling to learn that nothing is happening billions of light years away." In the context, that is not ET necessarily. But anyway, so that's an aside. So let's go on to real fast. I can't resist dropping XKCD into a talk. So what is real fast exactly? So this is a kind of a boring diagram, but if you're interested in the technology behind it, the VLA is built here in these boxes up here. It's basically a dedicated supercomputer for the explicit purpose of correlating the signals. It uses a commodity compute cluster at the back end of it to produce the final visibilities, which are then integrated to a time scale of typically seconds, and that is then served through an archive to the public. And our innovation here is that we've put a new cluster that's here, which is dedicated purely to sampling and having access to the memory space in that back-end compute cluster. So by having access to that compute cluster through the network, we can actually see the visibilities before they are integrated in time to that final stage. So we have access to millisecond timescale visibilities rather than second timescale visibilities. That's searched in a dedicated GPU cluster, real-time search pipeline, which can do a standard sort of parameterization of the searches similar to other systems, but in our case, we're searching images, not time frequency or sort of matched filter techniques that are traditionally used elsewhere. Another key thing to note about the way RealFast works is that it's a fully coherent, using all the information that's available in the visibilities at the detection, which is also what we're sharing and using to do the final localization. So that's different from how some of these two-stage detection algorithms work for other systems, where you actually detect on some sort of incoherent sum of the antennas or some other sort of reduced data form, and then you trigger the voltage recording to do the full analysis. In this case, we're doing a coherent detection and then a coherent localization with the same data. That becomes relevant when I talk about our discovery at the end, which is sort of at the limits of the sensitivity. So, quickly, I can also note here the development status, right? It's fully implemented. Basically, things are working as we expect. And then our plans for development, on the development side for the next, say, 6 months to a year, we're really pushing to get to low latency alerts. So we have a convolutional neural network that does real-time classification of our FRBs, helps us to sort the RFI that was very common in these domains from the real astrophysical transients. So we're hoping to push that out in the next few months. And then automatic archiving at the internet will help us to serve the data for those events rapidly to the public. And our plan is to have this be an FRB localization machine for the community. It's a value-added instrument for the community that's attached to the VLA. Where's our current status? So our observing status, this is accumulated observing time versus date. And so we started doing some initial work in June of last year. This is now distinct from the work we did with FRB 121102, where it was a dedicated, controlled experiment to observe the FRB. This is now a purely commensal experiment where we are taking someone else's data, streaming it through the real fast cluster and processing in real time. So right around August of last year, we were able to deploy these new correlator modes of the VLA. So that's just the typical observer at the VLA would then set up their observing script in the web interface, and they would send it as they always would. But if they were observing in a particular kind of correlator mode, which is like a continuum correlator mode, typical of, say, observing faint radio sources throughout any sort of science case, they would then pick up this resource and then distribute data to our cluster. So once we turned that thing on, we started accumulating about quite a bit of data. So at a rate of about 14% of typical observing, that data is then streaming through this cluster for an FRB search. I did a calculation. It corresponds to about 800 terabytes of visibilities that have been searched by our cluster in the last 6 months or so. So that's pretty exciting. We are observing at bands from 1 to 12 gigahertz. Again, it's these continuum modes. And the one sort of critical struggle and challenge for us is that we're limited by this commodity compute cluster that the VLA uses for its standard visibility generation, this thing they call a CVE. And the compute power of that was not designed to do extremely high rate visibility generation. So we have sampling times that are relatively poor in comparison to other experiments. That limits our sensitivity. Our goals for the next 6 months, again, we're going to push that down to 5 milliseconds. Recently they upgraded the cluster in the back end of the VLA, so we hope to go faster. More correlator modes, so we know that we can do continuum observing really well. Some people like to do spectroscopy and other kinds of things in the VLA, so we'd like to have access to that data also, and that will help us push that 14% up to hopefully 30 or so percent. And then VLAS, is the VLA Sky Survey, is a big chunk of observing in the next year of the VLA, and if we get access to that, it'll be about 800 hours just in itself in the next 8 months or so. So, continuing on. What makes Real Fast novel? This is just an RA deck distribution of the latest snapshot of our candidates that come out. These are basically all noise-like events, so this is not a map of FRBs, unfortunately. But just to give you a sense of how our candidates distribute on the sky, we see things all over the sky because that's where people point the telescope. So, a nice way of saying that is it's a crowdsourced pointing selection. So we don't get to choose where we point the telescope for our FRB searches, but it does mean that people could pick surprising things for us to look at where we might find FRBs. So one thing I'd like to hopefully might come up in the panel when we're talking about what's a novel thing we'd like to do in the future with our efforts of theoretical work or observational work is to think about kind of what's that real surprising association we might find in the near future. It might be it comes from someone looking at a supernova remnant or something that you don't expect to have FRBs. Similarly, frequency selection is out of our control, but that means we're observing frequency bands that are not commonly used. And so that means we might have something to say about the rate of FRBs as a function of frequency, for example. Sensitivity, if we can get our sampling time down, will be novel in the sensitivity domain. And I think it's quite fun that we're doing simultaneous slow and fast observing, which means we can do things like studying persistent sources associated with FRBs. So non-commensal science. I'll go over this very briefly, but just to highlight some of the things that we're doing with this sort of system that is not explicitly commensal transient search. Actually, I'm pretty happy about this one. This is a study of, again, looking at a different class of radio transient, superluminous supernovae, and hoping that we can find both persistent emission from the late time emission of the supernova or potentially an FRB, right? So it might be that these exotic supernovae are actually generating sources of FRBs. And in this case, we didn't find anything, but nonetheless, the persistent imaging all right, thank you. Better? Test, test. Thanks. Okay. So we didn't see any bursts, and I was really scratching my head for a while. Why didn't we get anything? So I did look at the period of activity, and this is where we observed. So sometimes you just don't get the breaks, but the hope is that with more time on sky, we might pull this out again. And we're still working quite a lot with the CHIME FRB team, and they've been very, very supportive of the effort at the VLA. Okay, commensal discoveries. I'll skip ahead a bit, but we are finding things. So our first discovery was actually the galactic center magnetar, which is not really a discovery; it's a rediscovery. But it's a dispersion measure of 1781 in this case. So we know we can find highly dispersed things. This is an example of a dedispersed dynamic spectrum where this is the Stokes eye in the middle. And then the image itself shows someone was pointed at the galactic center, and so it's right in the center of the image there. This is like a zoom in here. And what else? We actually were observing commensally with a program. Someone was using a program to look for a radio emission associated with a Fermi unidentified source. So there's a sort of cottage industry of trying to infer the nature of these Fermi unidentified sources. And by looking at the radio properties of sources in that error region, you can then hopefully look for steep spectrum sources, compact sources that can be indicative of a millisecond pulsar, perhaps. In our case, we shortcutted the whole inference problem and found bursts that are associated with that Fermi source. So that was a bit of a surprise. We found 5 bursts, no period, but we're working on the analysis and hopefully can say something about what is causing that Fermi, the high energy emission. And then the one I'm excited to share today is actually we're going to call it FRB 190613. It is a tentative detection, which we're working very hard to really make a robust and good argument about why we think this is valid. But it is definitely a faint one, and so I'll try to just briefly explain why we think it's good. This is frequency time again. Dedispersed pulse shows a little bit of an enhanced emission here. It's corresponding to sort of a false alarm rate of about 1 in a few hundred or 1 in 500 or so. When you take that spectrum and you slice it here, you get this sort of excess that spans a few hundred megahertz in frequency. Definitely not interference, definitely not a calibration issue, so we have some confidence in the analysis itself. But when you sample hundreds of dispersion measures for over 800 terabytes of data, you're going to get noise-like things that exceed some very, very high threshold. So our work is to really understand the noise properties very, very well before we can call this an FRB. But we've done that. We think we have a pretty good idea of the noise properties and what's happening here. What's really, that motivated us to follow up on it in the optical. What really pushed it over for us was that, so here's the sort of false alarm rate analysis. What really pushed it over for us is that we triggered optical observing working with Xavier Prochaska, and we found a very low probability association. So we have a host galaxy. This is a somewhat out-of-date plot, but we have a better localization than here. It's actually shifted over a bit recently. But there's a sort of a 1 in 20 chance that would happen by chance, the association of the radio source with a host galaxy. And that also corresponds, that host galaxy has a redshift that corresponds to the dispersion measure that we measured. So 3 things that sort of coincide with a pretty nice picture of having a very weak, very distant FRB. If that whole picture holds up and it holds together, we're going to have perhaps the most distant localized FRB, so that the upper range of this uncertainty would correspond to that, and the dispersion measure corresponds to the highest DM localized FRB. And the host galaxy is something like 10 to the 10 solar masses with a low star formation rate. So the exact star formation rate is still TBD, but it's going to be somewhere in that the center of the plots that we've seen earlier with star formation rate and stellar mass. And some oh yeah, this is SED modeling. So we only have 3 bands so far, but we're working on more follow-up in the IR that will hopefully more strongly constrain the photometric redshift. No obvious spectral lines in the spectrum that we've recorded for this host. So my last, well, I'm out of time. Speculations for the future, just briefly say, for some reasonable expectations for the population, we expect to have, at lower frequencies, a few FRBs per year. That's kind of our goal, our expectation for this. At higher frequencies, we also have a shot at finding and discovering blindly FRBs. But a big part of our strategy is definitely focusing on the repeating FRBs because that's the VLA strength, it's high sensitivity, not survey is not necessarily our strength. And then also, again, thinking about the pointing locations and the selection biases that come with that, we think there could be some potential for really exciting discoveries that come through someone else's selection of the pointing location. So with that, I'll stop. Thank you.